Good morning, everyone.
Morning.
Morning.
Let me first tell you that there's nothing better than starting my birthday by presenting my brainchild, Everix, which is really giving a meaning to my existence in this world. So I appreciate NASA iTech family for giving me this opportunity. All right. So my name is Human, and I'm the CEO and founder of Everix Optical Filters. Can we go to the next slide, please? Thank you. Where we transform plastic into gold. Very simply. Day in and day out, we transfer plastic into gold. But we don't do that chemically. We do that economically. We start with inexpensive pellets of optical-grade plastic materials, and we turn it into a material that is called thin-film optical filters that is at least 20 times more valuable than gold, based on the retail price that we're currently selling this at. So let's first talk about what optical filters are and why they're so necessary. So you can think about our sunglasses as a very simple optical filter that are basically filtering out certain portions of the light spectrum out of what goes through. But those are usually colored plastic or glass materials. They have multiple applications, but they're considered low-performance optical filters. Because as you can see on the left-hand side in this slide, their touch on the spectrum is not that selective. They usually have a very broad touch on the spectrum of light. Whereas in many high-tech applications, you want to have very, very selective filtering. You want to be able to pinpoint to a very specific frequency of light or a very narrow range, either block that and transmit the rest of the light spectrum, or transmit that narrow range and block the rest of it. And we'll talk about a few examples of this in the next couple of slides. But the challenge is that these higher performance optical filters are only possible through assembling a very large number of really thin nano layers on the top of each other and engineer them to tailor that spectrum. And their prices come out to a very, very high price, and they're a very wide range, but $1,000 per square inch is a very typical price of a very high performance filter. Can we go back to the previous one? Oh, there we go, this is working again. So let's pick a couple of examples here, and I'll be happy to come back to this slide and explain more examples. Let's go with smartwatches. So there is this technique called fluorescence imaging and sensing that has been used for the past couple of decades, but it's always behind the scenes. We don't get to see that. When you go to a test lab to get some blood work done, this is the technique that they use behind the scenes to detect infection, to detect cancer, and all kinds of things, even allergens, and many other conditions are detected with this method. And these systems use multiple pieces of optical filters. And these are very expensive. You're talking about a few $1,000s per instrument. Now there's a trend to bring that same technique to very small size benchtop point of care devices. They're going further to incorporate that into wearable and portable devices. They're incorporating this into next generation smartwatches so you can monitor more and more health conditions real time and completely non-invasively. And some of our customers are actually going as far as conceptualizing disposable versions of this. So you can just pick up a device from Walgreens or CVS and, check for cancer or infection and throw it out. So none of that would be possible if there is no economic and a scalable way of making optical filters, and that's what we do. Let's pick another example. Earlier yesterday, we talked about autonomy being a big deal for space. Autonomous cars, anything autonomous, robots, drones, autonomous cars, they all have these sensors called LiDARs, and they all use some type of range finding. So they shoot a laser light out to the environment, they map out or they range the distance, and that laser light comes back to the sensor. And you want to have a filter that is filtering out all of the noise in the background, which is basically all of the ambient light, and only focus on detecting that laser line. Another example. Let's leave Earth and go to space. So the same continuous health monitoring could be very important for astronauts. Imagine that same type of device incorporated into astronauts' suits. we've had direct requests from two different groups at NASA, one wanting our filters for some applications on the multi-junction solar cells, and another one for preventing certain thermal damages to the systems that are looking near the sun. And all of that light and heat focused into the system can actually create some damages there. So by having the right type of filter, you can filter that out and prevent damages. So we talked about these filters being so expensive, but the core reason, the underlying reason why they're so expensive is the way they are traditionally manufactured. You place substrates or lenses in a vacuum chamber, and then you put this on a really high vacuum, and you create a vapor of these materials, and that vapor sits on the substrate one atomic layer at a time. And you alternate between multiple materials, and you end up with a multi-layer coating. That's how it has been traditionally made. So I had a few years of experience running one of those vacuum chambers and setting them up. And I remember how painful and elaborate and laborious that process was. At the same time, I had a few years of experience drawing optical fibers, micro and nanostructured optical fibers for non-telecommunication applications. So I started thinking that, well, perhaps there are ways that we can borrow features from this massively scalable process of optical fiber drawing, which has enabled our global internet now, and use that as scalability and lend it to really high performance optical filter manufacturing. And that's how our process works. Instead of building these nanolayers one thin layer at a time, we start off with a large scale assembly of all the multi-layers, and we just like pulling taffy, we just shrink all the layers down to the nanoscale that they're supposed to be. And you can see, at least in the version that we disclose publicly, it's a very simple process. I'm going to go back to the slide, to the previous slide. So the process is not only more than an order of magnitude more scalable than traditional filter coating, but we happen to have some side features that are of tremendous value to many of our customers. For example, the filters are naturally coming out very thin, between 5 to 20 times thinner than anything else on the market. And the reason is that instead of having to start with a thick glass substrate and deposit these layers on the top, we're really just creating the layers as standalone. And this is of tremendous value for some space applications, and you can imagine how valuable it is when you have a smartwatch that has 7 pieces of optical filters in it. And the material also comes out flexible if we want to. We can make it rigid too, but it also comes out flexible if needed. And that's of tremendous value when it comes to adding really high performance filtering features to any curved surfaces. We can think about domes or cylinders that cover military sensors or LiDAR sensors. You can think about eyewear lenses, either for consumer eyewear applications or for again, military helmets and things of that nature. What I'm holding here is an eyewear lens that has a layer of our filter incorporated into it that has about 100 layers, I believe. And it is designed to specifically filter out a very narrow range of the spectrum that is proven to be responsible for triggering migraine headache in 80% of migraine sufferers. It's just another typical example. A little bit of history. Everix is a journey that I started in my storage shed just a few years ago, where I built a prototype machine just for proof of concept. And over there, I proved the concept of being able to go from larger scale to smaller scale and still maintaining integrity of layers. And fast forward, I built a team and a facility, the picture that you saw in the previous slide. There we go. This one is one of our draw towers in our current facility. Next slide, please. We have a very holistic IP strategy, including a good amount of patents covering every aspect of the process. We've made sure that even we cannot think of a way around our own process, and we've protected everything there. We also have patents around the device aspect of our product, the certain use cases of the product, the equipment that we use to scale this, and also some trade secrets on how we turn all these 20, 30 different knobs in the machines to run the process successfully. Next slide, please. So I hope to this point I've established the fact that this is a platform technology. We customize the material to any customer need, and we sell this as a component to other OEMs. So we realized that as a smallest startup company, we don't have enough access to all of the market. So we decided to partner up with someone who has established name in the market, and we ended up partnering with Edmond Optics, which is one of the major distribution channels for optical components. They are carrying some, I believe, 35 to 40 different part numbers of ours, and it's a great opportunity to expose this product to a very wide audience and kind of listen to the market and see where the market is pulling this product in. And through that, and also our own direct sales to OEM customers, we have realized that the interface between biomed and consumer electronic is one that we need to pay special attention to. We have ongoing government-funded developments and also some funded by our strategic partners. And we're actually getting very close to being in the supply chain of some Fortune 50 customers for their next generation products as well. Next slide, please. So this is to summarize our strategy. Any filter that is on the simpler side of the spectrum in terms of the complexity and the number of layers, that's closer to our minimum viable product, and anything that's a smaller than eyewear lens size, again, we consider that closer to our minimum viable. So the bottom left corner is the area that we're currently focused on monetizing while we're developing more complex filters that are really in high demand, but they're more on the complex side. We're developing those with government and customer funds. And when it comes to really large aperture size filters, let's say filters for autoglass, for blocking heat from sun without blocking the visibility of the driver. So those kind of applications will be partnering, and we are partnering with very major players in the film industry to give a license of our technology or do joint venturing. Next slide, please. So some financial projections. The idea here is to keep Everix focused on selling to really large OEM customers. So we have a pipeline of customers, and the goal is to narrow down to a handful of really large customers, producing over $35 million in 5 years. And the revenue per employee and revenue per square foot of facility is projected to be anywhere from 2x to 10x better than the average of our industry. Next slide, please. We've invested some seven-figure amounts in the business so far, about a third coming from myself and money that I've borrowed from family, and the rest coming from strategic investors and a great group of angel investors. And as we speak, we're raising a $4 million round as our final round of funding in order to hit all of our milestones in our next facility. Next slide, please. We've got a great team of 10 full-time operational people, including myself and Blair on the finance side. Andy runs our operation and manufacturing, Yana on quality side, Justin on automation side, and we have 5 other amazing technicians who are helping us on with running the day-to-day operation. So we have a really young team, but we're all very talented, excluding me. And you know, the whole team is very driven as well. And we also have an amazing group of advisors and board of directors who are basically checking the sanity of all of our decisions and making sure that we're on the right track. I'll just give an example. Mark Whippich is expert in selling to multi-billion-dollar companies. You know, his first job out of college was actually running some of these vacuum chambers to make filters. Sam is the president of Edmond Optics. James is a former VP of another very major, massive optical coating company. He's now on our board of advisors and also an investor. So, next slide, please. We are envisioning that along the way, we will have multiple partial exit opportunities for the areas that we don't want to enter directly. And this is mainly around really large format and large size optical filters. and the rest of it will be kept in-house, and we envision that there are multiple potential acquirers for the core of the business that's focused on really high margin and small size filters. I think that's all I had. Thank you.
The judges have about 15 minutes for questions and answers.
Yeah, can you say something about what wavelengths you can filter currently and where you're planning to go?
Sure. So to the extent that I can disclose publicly, the polymer materials that we currently use, they're transparent up to about 1.7 microns, starting from about 350 nanometers. So it covers the entire visible and some of the infrared, but we have successfully incorporated very transparent infrared materials into our process as well. So I would say within the next year or so, we can go all the way to about 15 microns.
Hi, I have a question for you. Have you considered partnering with optical companies like Zeiss?
Absolutely. Actually, if we go back to the Exodus slide, so we were considering companies in that category as potential acquirers and also strategic partners. And in fact, we're working with one of those large lens manufacturers already on developing certain filters for consumer eyewear.
Could this be utilized in indoor vertical farming in any way, in terms of the fact that the filtering of certain lights can enhance growth? It might not be for the vertical indoor, because that's maybe LED, maybe that was the wrong question. Externally, for greenhouses, by filtering the certain specific aspects for certain plants, it could be enhance the growth of those plants. Is that something you've considered?
Absolutely. Actually, there are two ways of doing that. One is by having passive optical filters that are just filtering out all the extra light and only letting the useful light go through. And temperature is a big deal. So if you can get rid of all the unnecessary light, that's already a plus. And there are also ways of incorporating active materials in these filters to enhance the emission in the ranges that are useful. Our current focus is on passive filters, unless there's enough funding behind a new R&D line.
Have you done any work with the Department of Defense?
We have just recently started some works with the Air Force, but we're open to more opportunities.
What Air Force, where were you connected with the Air Force?
So we can definitely talk more details in the private sessions, but up in Dayton, Ohio.
I have a great subject matter expert for you that left AFRL, and I believe this would be a good fit for the Seeker division. Mm-hmm. He was over the LiDARs and seeing the target, and I think he would be a great guy for you to talk to.
I appreciate that.
So he's a friend of mine, and he's retired, and I think he'd be great for you to.
Wonderful. I appreciate it. Thanks.
Thanks very much.
Thank you.